The presentation also. On the right-hand side is an elevation scheme for that mountain. Each of the black dots is a dust devil point. I got this out of a Reese et al. Paper in which they propose a GT effect occurring at the top of this mountain here to explain the greenhouse thermophoresis effect, to explain the lifting of the dust. But all that effect does is it says the dust will lift. It doesn't explain the spinning formation or why it should look like dust devils up and down the mountain. It's continuous. So you shouldn't need a special effect. Next. Okay. Interestingly enough, if you have a dust storm, in this case it's a regional one, at an altitude of 75 miles, the dynamic pressure increased by a factor of 5.6 in 4 weeks. Now, on the topic of that, there was also unexpectedly high deceleration of both the Mars Reconnaissance Orbiter and the Mars Global Surveyor. The Mars Global Surveyor was the one that recorded that bullet above. Now, the Mars Reconnaissance Orbiter, on the other hand, found that there was over 3 times more atmosphere than expected over the South Pole, and that caused them severe problems. Next. Okay. Now, you may all be thinking, well, we should know what the pressure is. The landers measured it. Well, here's the first caveat. All the pressure sensors were linked to dust filters. These dust filters could easily clog if they were higher pressure. There's no way to change them also. Now, if this were the size of a dime, to scale of that, the red dot would be the Mars Viking and Pathfinder dust filters, and the dot below that, really tiny, 10 square millimeters, is a Phoenix dust filter. Next. Okay. There are also disagreements in between radial occultation and scale height calculation for the minimum pressure on Mars. I'll explain that more later, but the difference is several 100%. What you have here is a landing ellipse. Now, on the topic of that, the last 4 landers were downrange by 13.4 to 27 kilometers. If you're trying to land the shuttle on Earth and you're off by that much, that would be considered a disaster, not a success. NASA's Pursoon Desai, who works on these, requested help with this. His theory is that the pressure at 50 kilometers is 40% less, but 5% more at the surface because there's only a finite amount of atmosphere. But what I'm calling for here is not that type of thing. I'm talking about several 100% higher pressure. Next. Okay, wind data. 50% of the landers could not really get wind data. They had a meteorological package. The picture on the left is what an anemometer would look like. Now, Pathfinder had an anemometer, 1996 mission. They could not calibrate the anemometer no matter what they tried because this might be due to a misunderstanding of pressure. To calibrate an anemometer, you need to know the pressure. Okay, on the right there is the Phoenix Telltale. This was the wind device sent on Phoenix. They could not afford an anemometer, apparently, despite $37 million for the meteorological package. Basically, all it is, it's a very thin string of Kevlar fiber with a bucket at the end. The bucket catches the wind, and the deflection angle tells you what the wind speed is, but it only has 20 to 40% accuracy, and for any wind speeds greater than 22 miles an hour, it goes horizontal. Basically, it only tells you this is the direction of the wind, nothing else. Click the link, I guess. Does it let you do that or not? No, I can't do that. Oh, that link would actually show this blowing around in what's supposed to be a vacuum, back and forth, back and forth. Okay, next. All right, there's also snow on Mars. Now, in the clouds, the ice particle sizes that are observed are 2 microns, but the global circulation models, which are the weather forecasting systems, call for 20 to 30 microns. That's just wrong. That's a discrepancy there. Now, they might be trying to use these bigger ice particles because the smaller ones might sublimate before they hit the surface. But it's also argued that if there were higher pressure, there should be bigger particles. But then again, we should note that the sampling rate for the data collection for this type of thing is very small on Mars. Just trying to point out the global circulation models, which are the weather forecasting systems, don't really work. Next. Okay. Back to the dust devils. Dust devils are driven by pressure differentials. If there is so little air on Mars, how can there be enough change in pressure to generate them at all? What I'm talking about here is relative pressure drops, in addition to absolute ones. Over 30 dust devils hit the Phoenix in 150 days. So something the size of a car got hit by a dust devil about once every 5 days. Mars Pathfinder before that was hit about once a day by a dust devil. Next. Wait, that's backboard. Okay. All right, the terrestrial and Martian dust devils are very similar in about every aspect. The latitudes of formation are mostly 37 and 65 north and south on both planets, and since both planets have about the same axial tilt, that's really about the same thing they correspond to. The season is most commonly either late spring or summer for formation. All dust devils have electrical properties. As will be shown later, the dust devils, you'll notice, will have a little bit of a glow. As much as a 0.8 megavolt effect was associated with one of these. And the shape and size are the same. They can get a lot bigger on Mars, despite the fact it's supposed to be a vacuum, 50 times wider and 10 times taller. And they usually form around noon when you have peak solar insolation or heating. Next. Okay, as mentioned earlier, the dust devil wind speed is usually about 13 miles an hour or 6 meters per second. The core temperature increase on both planets is about 10 Kelvin, usually. It can be as high as that. That is the difference in temperature in between the dust devil and outside the dust devil is that. That's equivalent to 10 Celsius. The dust particle size, that is the stuff that's being lifted, is the same, about 1 micron. But with the low pressure on Mars, it would require 1,118 mile-an-hour winds to lift that dust, observed. So supposedly an effect called saltation plays a role here. What that is larger particles that are easier to entrain, that are about 80 to 100 microns, are lifted, impact the ground, knock out these smaller particles, and entrain them into the wind. Reading those 2004 there. Next. Oh, if you just sit down. Okay, absolute pressure drop. For a dust devil at the Phoenix lander, the maximum pressure drop there was 0.003 millibar. And for an Earth event at Utah, where a dust devil passed between 8 and 10 feet of microbarograph in the 50s, the drop was 1.354 millibars, which is 451 times greater than the Mars event. Now that's the glow I mentioned earlier, if you look at these dust devils on Mars. Next. Okay, the relative pressure drops are the important issue. For the Utah event, it was 0.148%. For the Phoenix event, it was 0.036%, which is a lot smaller. But there are also 75 drops recorded for Pathfinder between 0.075 and 0.75%. But typically, the relative pressure drops on Mars are a lot lower. Next. Okay, I mentioned the scale height earlier. Scale height is the pressure required by a parcel of air moved up or down the atmosphere at a constant temperature. According to Reed and Lewis 2004 in The Environment of a Desert Planet, it's a book, they say it works very well on Mars, and it does for a lot of things, but not for everything. Your pressure equals your original pressure times a negative exponential, where you have your height and your scale height constant. Scale height on Mars, the constant is about 10.8 kilometers. Some people also use 11 kilometers, but 10.8 is more accepted. That's how I got the pressure in our CMONs to be about a millibar. That's also well accepted. But again, the question being here is if NASA Ames could not replicate the dust devils at 10 millibars, how could they do it at 1 millibar? Okay, the chart here, it's on your handout. Slide 18.
Page 7.
Yeah, it's also on page 7 of the report. The report is on your right-hand side, I think, on your handout. Okay, the left-hand side here are the locations on Mars. The right-hand side are the pressures in millibars. Now, if you'll notice, most of the pressures are about a millibar for the highest mountains on Mars. The valleys can go as high as 12.5. The landers, these are pretty much on the mark if you account for the time of year. I need to, next, I guess, next slide. Okay, the scale height, I use it for the landers, predict the pressures on the mark. But for the mountains, where you would have the minimum pressure on Mars, it disagrees with radio occultation. Radio occultation played an important role in the sensors and the selection, as will be shown later. Next. Okay, radio occultation is simple. The planet must be in between the orbiter or flyby and Earth. Now, radio waves are sent through the atmosphere, and depending on the index of refraction you're getting, like the angles and stuff, you can calculate the pressure, supposedly. The minimum pressures recorded by all the mariners range between 2.8 and 4.1 millibars. But my scale height calculations reveal that the pressure should be about a millibar at some of the higher mountains, which is about 0.86 millibar for Olympus Mons. Now that's about a 300 to 400% difference. That's huge. And even if you account for the time of year, my scale height calculations would only change by maybe 20-30%, which is not enough to account for that. And also, Mariner 4, which was a distant flyby, was wrong about daytime temperature at the equator by 95 Celsius. It's a lot. Next. Okay, what I'm going to show you here, storm-like formation can form over CMONs on the same time of year, despite the fact that the pressure there at the bottom of the storm is about 1/1000th of Earth pressure, and as you go up, it will become about 1/10,000th of Earth pressure. Now, what's in between the yellow line shows you roughly what the size of the wall is. The red line shows the edges of the caldera mountain here. Well, the question is, have something that's this vigorous form at that pressure? I don't think it's possible. You would have to have higher pressure to do it. Next. Okay. Only 4 landers could measure pressure, and coincidentally, 4 landers had meteorological packages. None could measure 18 millibars. 2 are limited to 12. Now, these limited pressure ranges were all based off the radio occultation, which disagrees with my scale height calculations by several 100%. Next. Okay, starting with these, I'm going to pick apart the pressure instrumentation here. The first two, 0 to 18 millibar range, Vikings 1 and 2. The third one was a Pathfinder 0 to 12 millibars. Now, there was a Tavis TAD that said a sensor was ordered that could measure up to Earth pressure, but it was supposedly kept on Earth. See page 9 of my Enigma report, and I have the CAD, if you don't mind switching for that real quickly. It's going to say 0 to 15 psi, which converts to that figure in millibars. I'm going to just find it. Bottom right-hand corner.
Sorry. Okay.
Yeah, and just go to that, zoom in. This one, I can't really see. Yeah, the top one. Okay, move over. I got at least some Metavis representative as part of these people. 0 to 15 psi, in case you're curious. It's on the handout and the report also. Okay, back to the PowerPoint. Down there, middle, bottom, from current slide. Okay, next slide. All right. Last meteorological package and pressure sensor on Mars, the Phoenix lander, made by the Finnish Meteorological Institute. Now, in a report in 2009, they stated we should find out how the pressure tube is mounted in the spacecraft and if there are additional filters, etc. They built this thing. It's supposed to have one pressure dust filter. Now, the left-hand side, that is an intake tube up there. The thing underneath P-RAW with the red line pointing to it is the dust filter. That's the schematic of what it would look like. So, next. I'll explain why they had this problem also. International Traffic and Arms Regulations prohibits the sharing of certain information. Now, these bear caps, if you could actually use them theoretically for nuclear weapons for detonation altitude, that might be why. But it was found in a Taylor et al. Paper, Taylor worked on the sensor, that after Phoenix landed, it proved the actual thermal environment was worse than the worst expected case. Information on relocation of the heat source had not been provided initially due to ITAR restrictions. That really played around with their data and made for a lot of complaints. Next one. Okay, I contacted the FMI and what happened to their sensor. Something stinks. He said your nose smelled the real issue. That we at FMI did not know how our sensor is mounted in the spacecraft and how many additional filters there were. Shows that the exchange of information in between NASA and the foreign subcontractors did not work optimally in this mission. I don't think it really worked at all. Okay, next one. Okay, now this is real oddity. Would you expect for 55% of the days, the same days, year after year after year, 4 years, for the pressure data to be the same? Probably not, especially since the Martian year is about twice as long as an Earth year. Now, what you're seeing up there, these top two curves here, that's supposed to be 4 years, 4 curves, but it looks like one curve. You can't distinguish in between the lines. That's for day 167 of the year, or 190 of the year. The next one over is, again, over 100 days. Viking 2 is down here. That's 2 years. Next. All right, now what you're going to see here, the yellow shading is repeatable data. That's the time of the year when the data pretty much repeats. You may all be wondering, what is this discrepancy up here? This is for Viking 2. This discrepancy up there is due to the dust storm. Now, I superimposed the last lander, the Phoenix, with its pressure data on here, with the stars and the line in between them. It seems to fit the data on here well, a little bit too well, as I'll be showing. Go. Yeah, that's fine. Okay, what I'm going to do here is I'm going to go take data from the Phoenix lander. I'm going to take it to another part of the planet, another year, and a different elevation. I'm going to predict the pressure there to that precision. It's not very hard. Okay, the Phoenix landed at Sol 164. The black dots are the G data or the weather forecast. The red dots are the actual data, and the red line is the extrapolation. Now, the Phoenix died around Sol 300. I take the straight line extrapolation down to the same time of year when Pathfinder saw a dust devil. And if I account for the slight difference in height of a couple hundred meters, I can predict that pressure there to that precision. I have information on this in my report, pages 16 to 18, how I did the calculation. But I should be able to do it that easily. Okay, back to the ice cap. Byrne and Ingersol, one of the works at Caltech, stated that a CO2 residual ice cap with an area of 88,000 square kilometers could only contribute 0.36 millibar additional atmospheric pressure if completely sublimed. But the pressure swings of the Vikings are between 2.1 and 2.6 millibars. That's like an order of magnitude difference.
The residual cap is the thick permanent cap, not the seasonal cap, which the seasonal cap is responsible for the annual pressure.
Right, they're saying if they melted everything there, that would be the case.
That is the tiny little South Polar residual cap.
Yeah, that's the one. The South Pole is the one that has the carbon dioxide. The North Pole doesn't really have much of that. And actually, the South Pole is mostly water ice underneath that carbon dioxide layer.
But the seasonal cap is far larger and being exchanged continually between both poles.